Okay, so we will introduce a new quantity today, angular momentum. Okay. And so let me remind you what this is about. Do you guys remember Newton's second law? What is Newton's second law? So F equal to ma. But this was valid only under special circumstances. What was the correct form of Newton's second law? Right. So F was equal to time rate of change of momentum. Okay. And this guy reduced to that. When did it reduce to that? Yep. So this was according to chain rule, d by dt of m times linear momentum is m times v, and so this was equal to dm by dt times v plus m times dv by dt. Okay, so Newton's second law reduced to that when this term was 0. Okay, and in most cases, for most applications that we apply, the mass of an object is not changing, and so F equal to ma is valid in those cases. But this is the correct form of Newton's second law. Okay, so we will do this for rotational motion. What we'll do is we'll introduce a quantity that corresponds to this quantity. So this is linear momentum, and we'll introduce a quantity called angular momentum. And Newton's second law will be, so angular momentum will be denoted by L. And Newton's second law will be torque is equal to rate of change of angular momentum of a system. Okay. So this is Newton's second law for rotational motion, and that's what this chapter is about. Okay, that's the main point of this chapter. Okay, so that's where the title comes from. L is a vector, and it's the angular momentum of a system. Okay. All right. So, but before we do that, we'll introduce rolling motion. Okay. Then we'll introduce angular momentum. We'll talk about conservation of angular momentum. And what conservation of angular momentum will be is, okay, so this is telling you that the net torque, so the net torque acting on a system is equal to time rate of change of the angular momentum. You will see that net torque will equal the external torque acting on a system. Okay. And if the external torque acting on the system is 0, if this is 0, what does that tell you? If this is 0, dl by dt is 0, what does that mean? L is not a function of time. L is constant of time, constant in time. And that's conservation of angular momentum. Okay, that's what we mean by, okay. The conservation of angular momentum of a system means the angular momentum of a system is constant in time. Okay. And then we'll talk about precession of gyroscopes and tops. Okay. And we'll learn an interesting thing. That's why I bought this guy over here. Okay. So we'll look at that. All right. So let's first talk about rolling motion. Okay. Okay, so okay, we started off this course by talking about translational motion. When an object was translated, every point on the object had the same displacement, had the same velocity, same acceleration. Okay. And so we could treat this object as a point object. We treated all objects as point objects. So for instance, when you're driving your car, this point of your car is going at 80 miles an hour, this point is going at 80 miles an hour, and every point is going at 80 miles an hour, assuming you're not spinning and stuff like that. Okay? So we could treat your your car as a point object. So we did that for several chapters: translational motion, pure translation. And then you studied pure rotation. An object was rotating about a fixed axis, okay? So this was the axis and it was rotating. And now we're going to combine these two motions. Okay, I'm doing this here because I'm recording it. I'll show this to you in a second on a wheel. But now let's combine these two guys. So we'll just add up the vectors. We'll add this and that. That's that vector. We'll add this vector and that vector, which is this vector. And we'll add this vector, and that's the 0 vector. Okay, so when an object rolls without friction, without slipping, the point and the wheel that's in contact with the wheel, that's at rest. This is the center of mass velocity of the wheel, and this point is going at twice the velocity. Okay. So rolling without slipping is the sum of pure translational motion and a pure rotational motion. So rolling without slipping is a combination of rotation and translation. Okay, so let me show this to you now on a wheel. Right, so what we were saying was the following. Okay. So the first several chapters, what we did was we studied pure translational motion. Okay. Every point on the object was traveling with the same velocity, and so you treated this as a point object. Then we graduated to pure rotational motion. Okay, so here was a fixed axis. And in pure rotational motion, points on the opposite side of the axis are going equidistant or going with opposite velocities. So this guy's going, if he's going at 5 meters per second, this guy's going at minus 5 meters per second. This was pure rotation. Now, if you combine the two, what you get is rolling without slip. So that's rolling motion. All right, so if you combine the two, you get pure rolling motion, and so here's a, okay. So pure rolling, if an object is rolling, so as the object rolls, when the wheel has traveled a distance s, okay, so that is the arc length, the wheel has rotated through an angle theta. Okay, so the distance the wheel traveled is equal to r times the angle through which the wheel is rotated. Okay, and again in this formula, theta is in radians. Okay, so now if you take the time derivative of this gives you the center of mass velocity of the wheel. And that's equal to r. The radius of the wheel is not changing, is d theta by dt, and which is d theta by dt is omega, the rate at which the wheel is rotating. Okay. So the velocity of the wheel is r, the radius of the wheel, times the angular speed of the wheel. We mentioned this before. You guys have seen people with cars where they put large wheels on the cars. And the reason they do that is the following. See, the engine of the car can provide you a maximum rotation speed. So if you put a big wheel, you get a greater maximum speed for the car. Okay. So if your speedometer has a maximum of 150 miles an hour, you put a wheel that has twice the radius, you get 300 miles an hour. Okay. Now, I'm simplifying this, okay, so as you go faster, the drag forces on it on you tremendously increase, and so it's harder to do that. Okay. The drag forces go as your speed square, actually. All right, and the acceleration, if the wheel is accelerating, so if you have angular acceleration, the center of mass acceleration is given by the radius of the wheel times the angular acceleration. Okay? And that's what's related to the torque that your vehicle can provide. Okay. All right, now we've said that rolling motion is a combination of translation and is translational plus rotation. And we'll show that in this formula. Okay, so the kinetic energy, whenever an object is moving, it has kinetic energy. So when a wheel is rolling, it's rolling, this is the point of contact that's at rest, and it's rotating about that point. And then this point comes in contact, and it rotates about that point, and so on. Okay, that's rolling motion. Okay, so as it's rotating, you see every point on the wheel is moving, so it has kinetic energy. And the kinetic energy is 1/2 times the moment of inertia of this object about that point, and that's what this is. The moment of inertia about point P times the angular velocity square, so I omega square. All right, in the last chapter you saw that the moment of inertia about this axis is equal to the moment of inertia about the center of mass axis plus the mass of the object times this distance square, and that's what that is. Okay. So IP, the moment of inertia about this axis, is equal to the moment of inertia about this axis times the mass of the wheel times r squared. And that's all we've done. Replace this by that. And now this guy is, so this is 1/2 ICM omega square. And this is the kinetic energy of pure rotation, okay, rotation about this axis. And this is r omega is the velocity of the center of mass. So r square omega square is v center of mass square. So this is kinetic energy of pure rotation, and this is kinetic energy of pure translation. Okay, so rolling motion is pure rotation plus pure translation. Okay, so for an ideal wheel, so if you're going at constant velocity, there's no rolling friction. Okay. Well, it turns out that in real wheels, as you're rolling, this front of the wheel deforms and you have a slight friction in the opposite directions. So you have to keep pushing to keep an object rolling. Okay. But for an ideal wheel, if it's going at constant velocity, there's no rolling friction. And you will sometimes see this referred to as rolling friction subscript R. Okay. But in general, rolling friction is much less than sliding friction, is much less than kinetic friction, and of course less than static friction. That's why we have wheels. You know, when you have a wheel, it's easier to move an object because rolling friction is very small. Okay. But all right, so we're considering an ideal wheel. Okay, so when there's an ideal wheel, when it's going at constant velocity, there's no friction. But if you want to accelerate, okay, what is happening is, so we'll imagine your car is trying to spin this wheel faster and faster, and this point is not slipping. If it slips, then you can't accelerate. Okay. If this point is not slipping, what is preventing it from slipping? It's the static friction between the road and the wheel. And that is what's making you accelerate. So the static friction between the road and your wheel is what's making you accelerate. Okay, so a proof of this, you might see this if you guys ever watch drag racing, you know, on the quarter-mile strip. What do those guys do on the drag race before they burn their tires? Why do they burn their tires? I'm sorry? No, when they burn their tires, when the tires melt and get sticky, what they're doing is they're increasing the static coefficient of friction. So then this force can increase and they can accelerate faster. Okay? So the stickier the tire, the greater can your static friction be and the greater your acceleration. Okay, so that's what they're doing. What is the price you pay? What's that? You go through more tires, but to win a race, you don't care, right? Somebody else is paying for the tires.
You race?
No, I don't. But yeah, so, but I can go faster than you. No. All right. So when you accelerate, it's the static friction force between the road and your tires. That's what's accelerating you. Okay. All your engine does is try to rotate give you angular acceleration. Okay? And the way you translate that into linear acceleration is by making sure that the tire doesn't slip. The static friction force provides that. If your tire slips, then you're not going anywhere. Okay? All right, so now what we'll do is we'll make this cylinder roll down an incline. And if you want it rolling without slipping, then you need a static friction force. If there's no static friction force, for instance, if it's a ice cylinder on ice, then it'll just slip. It won't roll. Okay. So for it to roll without slipping, what you need is a static friction force. And then here's this component of the weight of the wheel. So this is mg sine theta. M is the mass of the object. Okay, so there's the component of the weight there, and there's the static friction force. Okay. So these are the two forces acting on it, and this minus its static friction force provides the acceleration of the center of mass of the object. Okay. And also, if you calculate the torques about this point, this guy has zero torque because his moment arm is zero, and the static friction force times R, that torque is equal to the moment of inertia about the center of mass. So you're calculating the torque about this point. This guy has zero torque. This force is R cross F. R times F is I times alpha, the angular acceleration of this guy. So as this guy is rolling down, it's accelerating. Okay, so and these two guys can be combined to give you the center of mass acceleration, the acceleration of the center of mass. Okay, the acceleration of the center of mass of an object rolling without slipping. This is rolling without slipping. If it starts slipping, then all bets are off. So for a wheel or any object rolling without slipping, the center of mass acceleration is g sine theta divided by 1 plus the moment of inertia about its center of mass divided by mr squared. All right. Now, why do I... Okay, so let me remind you about something else. So if you have an ice cube that's sliding on an incline, okay, frictionlessly, then the acceleration of this ice cube is g sine theta. Okay, we've sort of done an experiment like this in lab, except that we didn't slide ice cubes. What did we slide? I'm sorry? Cars. with tiny wheels. So essentially they simulated ice cubes. Okay. We had a massive car slide down an incline with wheels that were very light. That essentially simulated this. Okay. So you see the acceleration of this ice cube is that. Now if you get anything rolling, its acceleration is that divided by a number greater than 1. Okay, its acceleration is slower. So if you get an ice cube and a wheel to race down an incline, the ice cube will win. Okay? If anything is rolling, it's rolling down slower. Its acceleration is smaller than that of the ice cube. Okay, what else can you tell about this expression? The greater the moment of inertia, the smaller the acceleration. Okay? All right, so did you guys understand that? The greater the moment of inertia of the object, the smaller the acceleration. All right, so let's see if you guys can figure this out. Okay, so these guys are the same mass, same radius. Between these two guys, which one guy will reach first? So what decides moment of inertia? What decides this guy? Okay, so let me write down the formula. Moment of inertia is MI/RI squared. Okay, it's the mass of the little piece. You can break up the object into little pieces, and how far that piece is from the axis of rotation. Okay, so for instance, for an ice skater, when she spreads her arms, her moment of inertia is high, and when she brings her arms in, her moment of inertia is low. Okay, so for this guy, they have the same mass, but this mass is distributed further from the axis of rotation. So this guy has greater moment of inertia than this guy. So this guy's acceleration, okay, so that was the acceleration, and this is the velocity at the bottom. So smaller the moment of inertia, greater the velocity. This guy has smaller moment of inertia, and he'll reach first compared to that guy. Okay. All right, so anyway, for an object rolling down, the acceleration, so object rolling down without slipping, the acceleration is smaller than for an object sliding down without friction. Yeah. And it's smaller by this factor. Okay, so it turns out that the moments of inertia are, for this guy, the moment of inertia is 1/2 m r1 square plus r2 square. R1 is the inner radius and R2 is the outer radius. For this guy, it's 1/2 m r2 square. R2 is that radius. And for this guy, the moment of inertia is for this guy, it's 2/5 mr squared. Okay. So this guy has the least moment of inertia, and he has the least moment of inertia, and he'll be going the fastest. So he'll reach first, and then this guy, and well, it will depend on, okay, so this guy will reach first, and between these two guys, what did we say? He has greater moment of inertia. Oh, so this guy will reach second and this guy will reach last. Okay. All right, we've already defined torques. Okay, so forces give you linear acceleration, torques give you angular acceleration. Okay. Torques make objects rotate. Okay, so the effect of a force, so the torque of a force So you calculate the torque about a point. So if you apply a force like that at this point, the torque is R cross F. R cross F. R is a vector from the point about which you're calculating the torque. You can calculate the torque about any point. Okay, so, and R is the vector. So if you want to calculate torque about this point for this force, then that is the vector R. If you want to, for this force, if you want to calculate the torque about this point, then R would be that. Okay, if you want to calculate about this point, R would be this. Okay, so you can calculate about any point. All right, so the torque of this force is R cross F. It's a cross product. Yep. And what will be the units of torque? What are the units of force? Newtons. What are the units of distance? Meters. So the units of torque would be Newton meters. Okay, and that's the SI unit. In British units, this is measured in pounds, and that's in feet. So in your cars, the torques are foot-pounds. Okay? That's what you see. All right, and we'll define angular momentum. Angular momentum is denoted by L. Okay, and similarly, so angular momentum is defined as R cross P. Okay, so if an object is going at velocity v, its linear momentum is m times v. And if you want to calculate its angular momentum about this point, it's R cross P. You can calculate the angular momentum similarly about any point. If you wanted to calculate about this point, that would be R. If you wanted to calculate it about this point, that would be R. Okay, so angular momentum is R cross P. Angular momentum about that point is R cross P. And it is a vector. And like we've seen about the rule, using your right hand, L is R cross P. Here is R. R cross P. If you turn from the first vector to the second vector, R cross P, using your right hand, your thumb points in the direction of the cross product. Okay, so if you turn a screw from R to P, it moves in that direction. That's the direction of the vector. Okay, so that's the direction of L. Okay, again, L, the angular momentum is in a plane perpendicular to the two vectors contained, the plane perpendicular to R and V. Okay. Okay, so now we'll show you the derivation of Newton's second law for a very simple case, and then obviously it'll be, and we'll just state that it's valid in the general case. Okay, so here's a point particle, and we apply a force on it. We're referring everything to this coordinate system. Okay, so here's a point particle, and we apply a force on it. What does the force do? It makes the object accelerate. Okay, so F will equal to dP by dt. Okay, the force applied will equal to dP by dt. Okay. Now what we'll do is we'll just calculate the torque of this force about this point, about the origin. So the net force equal to dP by dt. And now we'll calculate the torque of this force. So the torque of this force is R cross F. And so since if you hit this guy with a hammer, you got to hit this guy with the same hammer. R cross F is R cross dP by dt. Okay. Now here's the thing about cross products. Anybody remember what A cross A is? 0. Okay. Any vector crossed with itself is 0. Okay. So watch this. There's R cross P. dr by dt is the velocity. Velocity is momentum divided by mass. Okay, so this guy is momentum divided by that, and P cross P is 0. So this term is 0. So I'm free to add that. because this is 0, so I just added that to that. Well, why did I add that to that? Because now, see, I can apply the chain rule. This is equal to d by dt of r cross p, because that was the first term, and then this is the second term. Well, why did I do that? Well, this is something that we know. This is L, the angular momentum. So you see, the torque of a force is equal to time rate of change of angular momentum of the system. Okay, so here is Newton's second law. Torque acting on a system is equal to time rate of change of angular momentum of the system. Okay. So there is Newton's second law for rotational motion. We've derived this in a very simple case, but it's valid in general. Okay. Okay, this Newton's second law what was it applied to, applicable to? Was it applicable to a particle? Was it applicable to a system? It's applicable to everything. A system of particles, it's applicable to a single particle. Just like that, this guy is also applicable to a single particle. It's applicable to a system of particles and so on. Okay, and that's what we're going to say here. Okay, so if you have a bunch of particles, the angular momentum, these are vectors, so you can just add them. Angular momentum of particle 1 plus angular momentum of particle 2, that's the angular momentum of the system. Okay, this was torque acting on particle 1 was equal to time rate of change of angular momentum of that guy. You add up all the torques, that's the net torque on the system. Okay, so the net torque on a system is equal to time rate of change of angular momentum of the system. Okay, so just like that, this formula is applicable to a single particle or a system of particles. Okay. All right. So Newton's second law was net torque was equal to time rate of change of angular momentum. Okay. Now net torque is torque due to internal forces plus torque due to external forces. That's what this is saying. And if there are any internal forces are always equal and opposite. Okay. So the torque due to these guys, you can calculate them about any point and they'll always add up to 0. This will always be 0. So the net torque on a system is just equal to the external torque on the system. Torque due to external forces. Okay? And so now we've simplified Newton's second law to that. Instead of writing net torque, you can just write external torque is equal to dl by dt. Okay? All right, and again, we do this because now it'll help you see things. Okay, so any torques associated with internal forces are always 0. They add up to 0. Okay. Okay. Now you saw that torques depend on the choice of axis. So does the angular momentum. Okay. So this depends on the choice about which you're calculating. This also depends on the choice about which you're calculating. So for this to be valid, okay, both torque and angular momentum depend on the choice of the origin. Okay, so however the relationship between is independent of the choice of the origin if the center of mass of the system is not accelerating. Okay, if the center of mass is not accelerating, you can calculate it about any point, and as long as you're calculating about the same point, this equation is valid. It turns out that if you're calculating about the center of mass for an axis passing through the center of mass, net external torque acting on a system equals the time rate of change of angular momentum. This guy is always valid as long as you're calculating about the center of mass. Okay. Okay, so that's what we'll assume that is always, we'll always calculate about the center of mass, and this will always be valid, whether the center of mass is accelerating or not. Okay. All right, now we'll consider a simple case. So, for instance, a planet going around the star, okay, a particle moving in a circular orbit. The angular momentum of this planet is r cross p. P is a vector in that direction. And if it's going in a circular orbit, the magnitude of L is mvr. Okay? And again, here is r cross p. It would be L would be coming out of the plane. Okay, it will be perpendicular to the plane. If it's going counterclockwise, it'll be in the z direction. L will be in the z direction. The magnitude of the angular momentum is mvr. Yeah. So for a particle going in a circular orbit, that's that. Okay, so it turns out that for planetary motion, this is one of the laws that Kepler found. For planetary motion, he didn't realize this, but it turns out that the angular momentum of a planet is constant. Okay? So as most planets go in elliptical orbits, as you come closer to the star, as r decreases, the planet moves faster. Okay. Okay, so here's a rotating disk. It's rotating about its axis like that, and again, to find the direction of angular momentum, you use your right hand. If your fingers are pointing in the direction of rotation, your thumb points in the direction of the angular momentum. Okay. All right, so we'll break this disk into little pieces. So here is this little piece. The angular momentum of this little piece is its linear momentum, mv. Okay, so it's going in a circular orbit. It's mviri. And then if you want to add up the angular momentum of all the pieces, okay, by the way, vi is how far it is times omega. Okay, so this can be written as mri square omega. And if you want the angular momentum of the whole disk, then you add up the angular momentum of all those little pieces. Okay. And this is mri square omega. You're adding them up over all the little pieces. This guy is the moment of inertia. Omega is the same for everybody. Okay, so angular momentum for this guy, where I is not changing, is I times omega. Okay? And so the torque is equal to dl by dt, which is I times d omega by dt, which is I times alpha. Okay, so here is torque is I times alpha. Okay, this guy is the parallel of F equal to ma. Okay, when was this guy valid? When was this guy valid? Huh? No. When mass is constant, when mass is not changing. So just like that, torque is dl by dt. This is the correct form of Newton's second law for rotational motion. When I is not changing, just like when mass is not changing, okay, this reduces to that. Okay. Just like, when does this guy reduce to that? When mass is not changing. So this guy will reduce to that when moment of inertia is not changing. When does I change? So for a skater, if she's bringing her arms in and out, then I is changing. And then you have to apply the law. Okay? Okay. All right, now here are some fun topics. Okay, so it turns out that, so here is Newton's second law for rotational motion, dl by dt. Okay, so this equation has spectacular applications. It turns out that in nature, when random forces act, the torques of those forces generally are always zero about the center of mass. So when this is zero, the angular momentum of that system remains constant. And you'll see some spectacular applications of that. We'll come to that, but before that we do that, let's do this top. Okay. All right, so let me show this to you. Okay, so the center of mass of this object is there. That's where the weight of the object is acting. And if I let go of this, that weight will have a torque and it will topple it over. Now, that weight is not going to quit. What I'll do is I'll give this guy a spin. And now the same force, instead of it toppling, is making it precess. The same torque. Because now the object had an angular momentum, it's making it precess. Here's a spectacular application of it. Let me show you. All right. There's east. The sun rises in the east and sets in the west. Right, so let's say that is east. What is really happening? The earth is rotating. Okay. So the sun is fixed. And that's going up. All right, so really, we are rotating and we feel like the sky is rotating. Okay. So when I'm rotating, the sky is rotating, and if there's that star there, it appears in that part of the sky. So imagine you're a small ball, you're a cricket ball, and then you're surrounded, the sky is a huge beach ball, and as the baseball is rotating, it appears that the sky is rotating. So what point on the sky are fixed? I'm sorry? So there's the beach ball, that's the sky. Yeah. Everything on the sky is moving, but there's a couple of points that are not moving. So if you're rotating like this, that point is not moving. Axis of rotation. So if there happens to be a star there, that's stopping one star. That's stopping. Okay. So here's the Earth. It's spinning. And that's the North Star. Okay. Everything is rotating, and that North Star is not rotating. Now, when you applied a torque, what happened to this? So if you had a spinning object, a torque applied to it made it precess. Okay. So let's make sure we understand this. So the Earth, it's not a perfect sphere. The gravity of the moon and the sun applies a torque on this Earth. The Earth is spinning. So if the Earth was not spinning, this would not happen. And what the torque of these two guys are trying to do is they're going to try to topple the Earth. Remember, the axis is at 23 degrees, it's trying to topple it. So if the Earth was not spinning, its axis would just point like that. But because it's spinning, now the axis precesses it. Just like that. The Earth's axis. Do we get a proof of that? Okay. So how would you get the proof of that? If the Earth's axis is precession, okay, this precession is slow compared to that. Okay. So the Earth is going around the Sun as well, but this is tiny distances, and so for all practical purposes, that's the North Star. Okay. This is 1 year. Now, if the precession is slow, the North Star would change over time. Do you guys understand that? The Iraqi people were very good astronomers. Here is the North Star over time. 5,000 years ago, that was the North Star. Today, there is the North Star. And so this is an easy calculation. The precession time is 26,000 years. Okay. So the Earth's axis is precessing, and it takes 26,000 years to complete one precession. Okay, so what does that mean? Okay, so right now, in the northern hemisphere, it's summer. Okay? And 6 months later, the sun is shining directly here. So 6 months later, in December, it's winter here. But now you just learned that it's precessing once in 26,000 years. So in 13,000 years, if you're still living in America, you'll have summer in December. Right? Well, you can freeze yourself and come back in 13,000 years. You know that, don't you? Yeah. All right. So, that torque, yeah, did you still have your question?
No, that answers it.
Okay. All right, so if a top is spinning, the torque due to this force will make it precess. Okay. If it was not spinning, it'll just topple over. Okay. All right, this is the precession frequency. I'm not going to go through the derivation. And the precession frequency is, okay, mg was the weight of this object, r is this distance from the axis of rotation, and I omega is the angular velocity of the object. So the faster an object is spinning, the slower it precesses. Okay? And I can show that to you. You'll see this. And you might have experienced this with tops. I don't know if you guys ever played with top. So here it's spinning slowly, and then it'll precess faster. Okay? And now I'll make it spin faster. And the precession slows down. Okay? So the faster an object spins, the slower it precesses. Okay? That's what this formula is saying. Yep.
Is that simple?
Which one?
On the left side.
That's capital omega. This is little omega. It's like little a and capital A. Okay, so you can do these experiments. If you have a cat.
That's very expensive.
What? You don't like cats?
No, I have two.
You have two.
I'll
Well,
do it twice, don't worry.
Yeah, there you go. You can even watch it on YouTube. All right, so what's that?
No, it's nothing.
All right. So we said this is Newton's second law. The external torque acting on an object is equal to time rate of change of angular momentum of the object. Okay. Now, if the external torque is 0, then that means L is constant. Through the entire motion of the object, L will remain constant. And so you can watch this on YouTube. So, for instance, apparently you can do this. You can hold the cat by its feet, and as long as you drop it from about 3 feet, it'll land on its feet. Okay. So how does it do that is the question. Okay, remember, through the entire fall, the only force acting on him is, we're neglecting air resistance. The only force acting on him is gravity, which is acting through the center of mass. And if you're calculating the torques about the center of mass, that's 0. So the angular momentum about an axis passing through the center of mass must be 0. So if the cat doesn't do anything, its angular momentum is 0, and it'll land on its back. But the cat doesn't want to do that. So what does it do? So here's the cat. It's got to make sure its angular momentum is 0 through the entire fall. So what it does is it twists its tail, or the backside, and its body twists this way. And its angular momentum is 0 the entire way. Okay. So apparently people who have done experiments, it'll land on its feet as long as you drop more than 3 feet above, or something like that. Okay. Let's see if we can.
It's 3 feet below. Oh, it's 3 feet.
All right, that's taking too long to load. Anyway, you guys can go watch it. All right, so L remains constant. Okay. So here's why we. What happened? Man, I just bought a new iPad. This had better work. Crazy. This is crazy.